Okay, hello Professor. I'm going to be solving this problem for you. And my name is Isabel Murguia. So they tell us that a source, I'm going to go ahead and highlight some keywords. A source of strength M is located at a distance L from a vertical solid wall. The velocity potential, that is important for this incompressible and irrotational flow is given by, obviously this whole equation is very important. Part A, show that there is no flow through the wall. So we are going to assume that there is no flow through the wall. We essentially will just be proving that. And then for part B, determine the velocity distribution along the wall. So what this tells us, if they want us to determine the velocity distribution along the wall, this is the wall right here. Along the wall would be this way. So this would be the y component because it is in the y direction. So for part B, we're going to say the y component of velocity, which is what they're asking us. And then for part C, determine the pressure distribution along the wall, assuming P equals P naught, far from the source. Something that is important is this last statement, neglect the effect of the fluid weight on the pressure. Okay, so starting with that statement, neglect the effect of the fluid weight on the pressure. If they're telling us that the fluid weight has no effect, then we won't have any shear stress due to the fluid. So the shear stress, tau, is going to be equal to 0. And something that we do know from that, if we have no shearing stress, then this is going to be inviscid flow. And again, there is no shear stress because we are neglecting the effect of the fluid weight on the pressure. So that shear essentially is just not going to be existing. Okay, they also tell us that this is a source. So really quick, a source, again, we know from class and from the book that a source looks like this. We also know that a sink looks like that, everything going inwards, and a source would be everything going outwards. And then this variable right here, M, is defined as the strength of the source, or sink, in this case, a source, because they do tell us it is a source, and it appears to be, in fact, a source. So what we know about a source is that M will be positive, and then for a sink, M will be negative. And we do, another way to confirm this, besides the fact that they tell us it is a source, is we do see that this M is positive. There's no negative sign, so it is, in fact, a source. Okay, the rest of the key components. Okay, so velocity potential. Velocity potential is defined as phi. And phi does have components in the x direction, y direction, z direction, and t direction. So this is the components of the velocity potential. Because it is a 3D flow, which is why we have these components. It is not a 2D flow, otherwise we would not take into consideration the z component of the flow. So this is a three-dimensional flow. And again, they tell us that this is incompressible and irrotational. So what irrotational tells me is that the vorticity will be equal to 0. And they also tell us that it's incompressible. So something that we know about an incompressible irrotational fluid is that the gradient cross the velocity will be equal to 0. And this makes sense because the cross product right here, cross product, has to do with the rotation. So if it's equal to 0, then that means there is no rotation, which is correct because it is an irrotational fluid. So that makes sense. And another thing we have to find is this Laplace equation, which will be equal to 0. And this is only valid because the vorticity is equal to 0. Is equal to 0, so there's no rotation. If this vorticity was not equal to 0, then we could not use this Laplace equation. And this is just a little bit of background before I go into solving the problem. I think we are ready to solve though. So for part A, show that there is no flow along the wall. Oh, really quickly. V, which is the velocity potential, can be broken up into its components as U, the derivative of V with respect to the x, right, and then V, which will be the derivative of V with respect to y, and Z, which will be the derivative of V with respect to z. And phi can also be defined in this velocity times the gradient of phi. And this is just something that we learned. Phi can be defined through this. Okay, so just a little bit of background. Okay, so for part A, they're asking to show that there's no flow through the wall. So we know that u is equal to the derivative with respect to x of phi. Okay, and if we're talking about through the wall, this perpendicular is in the x direction. So that is why I used u equals d dx of phi, because we are talking about through the wall, which is the x component. Okay, so they did give us that whole equation of phi equals m, I'll just go ahead and write it out, m over 4 pi, this long thing, ln, feel free to fast forward through this, plus y squared plus ln of x plus l squared plus y squared. Okay, so that is phi. And we do want the u component of that. So in order to find the u component, we do have to take the derivative with respect to x of phi. So we will take the derivative with respect to x of this whole thing. Okay. So solving for that, I have solved this separately just for the sake of time and for math purposes. When we do that derivative, this is now going to be u, right? Because u is the derivative with respect to x of phi. So u will be equal to the derivative of that. So m over 4 pi is constant. We can pull it out when taking the derivative. And deriving this with respect to x, we do get 2 over x minus l divided by x minus l squared plus y squared plus 2 times x plus l over x plus l squared plus y squared. And I did get that from taking the derivative with d dx of ln is equal to 1 over x. So I did use that when solving. Okay, so we have this defined for u. However, we are looking to show that there's no flow through the wall. So the wall is right here. This is the origin. Okay, so this is where y begins and where x begins. So we can assume that this is 0, 0 for x and y. Knowing that and plugging in x equals 0 here, we can solve and get m over 4 pi times 2 times 0 minus l over 0 minus l squared plus y squared plus 2 times 0 plus l divided by 0 plus l squared plus y squared. Okay, and again, we are assuming that x is 0 because we are talking about the wall, which is at the origin. Solving through for that, we do get m over 4 pi times negative 2l over l squared plus y squared, right? This is negative l squared. Again, this is not difficult math. L squared plus y squared. Okay, so we get minus 2l plus 2l. That is 0, common denominator, right? We can combine. This will be 0. So we will get m over 4 pi times 0, which is just 0. And what is 0? We define this to be u, so u is equal to 0, which is what they asked us to prove. So there will be no flow through the wall. Right. And a way that we can kind of confirm this is looking at this diagram, the source. When we are finding the velocity potential, we're taking the derivative with respect to x. This x is actually just a straight line, right? It's constant. So the derivative of a constant is just equal to 0. So that does make sense when we do solve through, besides the fact that they did tell us that there will be no flow. So that confirms that. Part B, they're asking us now to determine the velocity distribution along the wall, which here I wrote that will be the y component of velocity, which the y component of the velocity will be equal to the derivative with respect to y of v. Okay, so same thing as we did earlier. We will take the derivative of v. So v will be equal to dy of this entire thing that they gave us in the problem, which I'm not going to recopy. I'm just going to leave it as derivative with respect to y of v. Doing this, we do get m over 4 pi, which again is still constant, so we can still pull it out. And now with respect to y, numerator is going to look a little bit different. X minus L squared plus y squared plus 2y over x plus L squared plus y squared. Okay, so this is a little bit different because we did solve with respect to y. Combining, we get over 4y over, So the wall, again, is still at position x equals 0 because it is at the origin. So we will be plugging that in here. So wherever I see x, I'm going to put 0, 0. Okay, and solving that, we will get a denominator of L squared plus y squared. Okay, these 4's cancel. So we get m over pi times y over L squared plus y squared. And this is equal to v, which is the y component of the velocity. So this is not equal to 0. And we can look back at the image and see in the y component, that makes sense because we are looking at now the derivative of these lines, right? And there is a slope there. It's not just a constant line. So it doesn't make sense that this will be, in fact, a value instead of just 0. And we also do notice that the denominator here is L squared plus y squared. So as these get bigger, this number gets smaller. So that is true because here we are looking at this x component, which is L. The further away we get from the source, what am I trying to say? Okay, so by definition, the further away you get from the source, the lower the velocity is going to be, right? So as y gets bigger and as L gets bigger, the velocity is going to be 0, or get closer to 0, or be smaller because we are moving away from the source. So that makes sense, which is how we can explain that. So that's part B. And I'm going to add a page here to be able to solve. Okay, part C. So for part C, they're asking us to determine the pressure distribution along the wall. So for that, we can use Bernoulli's equation. And for Bernoulli's equation, we do have to define 2 points. So I'm going to go ahead and define this point here as point 1, and this point there on the wall as point 2. Okay, because we are trying to find the pressure distribution along the wall. So it makes sense to have a point at the wall. So for part C, using Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GZ squared equals P2. Oops, I did not mean to put squared. This is GZ1. P2 plus 1/2 rho V2 squared plus rho GZ squared. So right off the bat, I can cancel these two terms because Z1 is equal to Z2, right? My 2 points, I define them to be on the same line, which is the x-axis. Something that they told us that we could define in based from they gave us in the problem was that P1 is equal to P naught. Okay, so we will be changing this P1 to P naught. And then something else that we know is that this is going to go to 0 because it is at the source. So the velocity at 1 is going to be equal to 0. So that term cancels. Okay, so we're left with P naught plus rho, P naught equals P2 plus 1/2 rho V2 squared. Okay, and we are solving for P2 because this is the point at the wall. So P2 is going to be equal to P naught minus 1/2 rho V2 squared. Okay, and then we did in part B find V2 to be, well, we solved for V, but this is actually V2 because it is at the wall. Hello, V2, so P naught minus 1/2 rho times m over pi times y over L squared plus y squared, and that quantity is squared. So solving through, we do get P2 is equal to P naught minus 1/2 rho m squared over pi squared. I'm just going to leave this in terms of pi and in terms of everything else, times y over L squared plus y squared squared. Okay, and we can distribute that squared, but I'm just going to leave it as that, just for simplicity. So this is my pressure distribution along the wall. Okay, and then again, why we were able to plug in that V value for the V component, or the velocity in the Y component, is because they're asking to determine the pressure distribution along the wall. So along the wall is still in the Y, which is why I was able to use V. Going back here. And I think that about sums it up. So going through the problem again. Oh, actually, something that I forgot to mention. So we used Bernoulli's equation. Why were we able to use Bernoulli's equation? We actually do have to say why. Bernoulli's equation can only be used if the fluid has steady flow. These are the conditions that we must satisfy: steady flow, it must be incompressible, inviscid, and it has to flow along a streamline. Flow along a streamline. So the steady flow, as mentioned earlier in the video, we do assume steady flow. They told us that it is incompressible. We know that it is inviscid because the shear stress is equal to 0 when they told us to neglect the fluid weight effect on pressure. And we do know that it flows along a streamline because in the beginning we were given that it is a source with these streamlines. So summarizing the problem, we started off with this problem. They defined V, which is the velocity potential, and they told us that the fluid was incompressible and irrotational, and that we could neglect the effect of fluid weight on the pressure. So part A, we did solve for u, which is the x component of the velocity potential. And this was because they told us to solve for the velocity going through the wall, which is in the x direction, perpendicular. We found that to be 0 because there was no flow through the wall, which they did tell us, but we also proved, because that's what the problem was asking us to do. For part B, we're finding the velocity distribution along the wall. So along the wall would be in the y component, right? Because it is in typical xy Cartesian coordinates. So solving through for that, we did get that v, the y component of the velocity, was equal to m over 4 pi times y over l squared plus y squared. And then for part C, we were able to use Bernoulli's equation due to satisfying these listed conditions. If these were not satisfied, we could not use Bernoulli's equation. And then I did define my points to be point 1 at the origin of the source and at point 2 to be the origin of the wall and the coordinate of x and y, which is the origin. And then for that, I was able to solve and get P2 is equal to this big mess, but we are leaving it in terms of variables, being that we have no numbers to plug in. Oops. And I said earlier, my name is Isabel Murguia. I will go ahead and sign for you. Go ahead and box that. Thank you for watching.